Well, with the open source toolchain, we can generate a Bitstream for the Zynq devices right on the Zynq itself. Yes, the Zynq is made of the PS part and the PL part, and the PS part runs Linux. We can run the open source toolchain OpenXC7 on the PS part and generate a Bitstream right on this, and program the PL fabric on the fly. Here we have a shell from a server port running of this pink Z1 board, and you can log in. I already have this OpenXC7 toolchain installed here. You can see that it runs on the ARM machine, but the main difficulty is there are so few memory, and this Ubuntu version is kind of old. So it took me a few trials and errors to get all those libraries the correct version. But now finally it's working, and we can activate by this one, and maybe the Python library as well. And then we should have all the tools now. And for the Bitstream generation, here we have some examples. It's just an ordinary FPGA project. There is a XDC file for this pink Z1. There is a code file. This is just a top module. We have a clock coming from the PS cores through the fabric, and we use it to drive a counter to blink 2 LEDs, while the other 2 LEDs are connected to the switch. There are some XC related things, but we don't use it for now. Here we have BUFG to buffer the clock output from the PS. At last, we have this PS7 module. We'll need to instantiate just like what we did in Vivado. Some ports are connected, but most are disconnected. Here we have the F clock, which drives our logic. Okay, and then we have the makefile. This is just an ordinary makefile for the OpenXC7 toolchain. We have this passes specified according to our case. We have uses here. We have this next point and root, a place and root. We have Bitstream generation. Well, the only thing is it needs a cheap database to run the toolchain, and the generation of this database requires a lot of memory. So that's why I say I almost have this one working, because this file is generated on another computer and copied to this machine, while other parts just runs locally on this pink Z1. Okay, we can then remove the existing file and then make it. Now we see uses running. Of course, it's kind of very slow. This one on an ordinary computer just takes less than 10 seconds. We can have here another shell to monitor the memory usage. Okay, now there's only 2 cores, and the memory usage now is okay, but we only have half a gigabyte of memory, and that's not a lot. Uses is still running. Yeah, there are some lags because it's using swap area. There's not enough memory, and this board has an SD card, which is very slow. It's literally burning the SD card right now. I don't know how long it can last. You can see the process jumping from running and maybe dead. I guess we're back now. Okay, now we are generating Bitstream. So it has finished, and we have here uh, a bitstream for this Zynq device. This can be loaded via JTAG, but since we are on the PS, and to load this into PL, we need to convert it into a binary format. Luckily, I found a tool, which is this one. It does the conversion quite well. Oh, what's that? Yeah, it's this one. Oh, the display is so bad. Oh no. This is a compiled version. It works just on ARM. And then I'll write the input as build top.bit and write the output to build top.bin. Okay. Here we have this top.bin, which is just a data file. And to load this into the fabric, we have another tool by Zynq. It's also an open source tool called this FPGA utils. It's just a source file. And it kind of plays with the system, sysfs file system to interface with the PL part. We can just use this line. And if you have an eye on this board, you can see after programming Bitstream, the two LEDs begins blinking. And if we flip the switch here, the other two LED will respond correctly. So this is a working bitstream for the PINZ1 generated on the Linux running on the PINZ1 with the open source toolchain OpenXC7. Actually, the speed is really fast. It only takes less than 100 milliseconds to load the bitstream.